Hello. Okay, today we are talking about this is chapter 3.3. Okay, part A. We're going to split this up into two parts. Today we're going to talk about how we know how many protons, neutrons, and electrons are in an atom, how we can count that, how we can use that periodic table to kind of associate with that, and yeah, and then how to figure out something called the average atomic mass, which is pretty cool, pretty interesting concept. So here are our objectives for today. Describe properties of protons, neutrons, and electrons. Calculate the number of protons, neutrons, and electrons in atoms given the atomic number and its mass number, and then calculate average atomic mass. So you should be able to, by the end of the day, criteria for success, right? State the charge, mass, location of each of the substance particles. Given a nuclear symbol, you can determine the number of protons, neutrons in the atom. Given the number of protons and neutrons, you can create the nuclear symbol. You notice these are kind of the inverse of each other. Given the masses and percent abundances of the isotopes of an element, you can calculate its average atomic mass. So a lot of little things you're going to be able to do today, and I think you're going to enjoy this lecture. Atomic number. Now, some of this is going to be a review. You learned a lot of this stuff in physical science, and you can go into a little more detail today. Atoms of different elements have different numbers of protons. Remember that it's the number of protons that really decides whether or not an element is one thing or another thing, okay? So if you want to say, what is the one determining factor that makes an element? The number of protons. Electron number can help you as far as its number of valence electrons or outer shell electrons. That can determine some properties of that particular element, but the element itself is all about the proton. So atomic number is the number of protons. All atoms that have the same element symbol have the same number of protons. Although they might have some other slightly different characteristics, they'll have the same number of protons if they're the same element. So we call it the atomic number, and you'll notice that we use the symbol Z, right? That little Z there, that's the symbol that we use to talk about the atomic number, okay? So if you see Z, you know atomic number, all right? And again, it identifies the element that is the one identifying characteristic. All right, so you're gonna hit the little pause it, okay? So see if you can answer these questions. Pause it when I'm out of the way. Okay, we're back. How many protons does oxygen have? If you look up the periodic table, you're going to see that oxygen has a little number 8 in the right-hand column. That number 8 is the number of protons that oxygen has, and that is its atomic number. How many protons in an atom of aluminum? Look at aluminum, find it. It's number 13 on the periodic table. Well, guess what? That number is the number of protons it has, right? An atom has 36 protons. What's its identity? We'll find 36 on the periodic table, and then you're going to find out that that element is krypton. Okay, so just look at the top right-hand number on the periodic table, and you're going to be able to figure that out. Okay, I'm going to pause for a second. I'm going to get a periodic table that I can hold up so you guys can see it. Okay. All right, so periodic table. Now, there are various different ones. I've given you a couple different ones that you can print off online, and you can see what they look like. But just wanted to make sure you guys can kind of get a look at it. And I said the top right-hand corner depends on the periodic table. This one has it just right up in the top middle, right? Oxygen we talked about, and then we talked about aluminum, right, number 13, and then we talked about krypton, number 36. So you can see a few different elements there, and those are their atomic numbers. All right, here we go. So have a periodic table accessible and ready to look at for any of these questions, right? Isotopes. Let's talk about isotopes. You guys know, I'm sure, what that comes from, right? Simpsons. Simpsons. All right, yeah. Isotopes. Elements have the same atomic number, but they have different numbers of neutrons. Okay, so an isotope has a different number of neutrons, same number of protons. So there's various different isotopes of each other. Some elements have a few isotopes. Some elements have like 30, 40, 50 isotopes, different numbers of neutrons, but they're still the same element. They still have the same basic properties, okay? Most elements have at least 2 isotopes. Like I said, some have a lot more. Here's an example. If we look at carbon, carbon's mass, we say, is 12.01 AMU. We haven't talked about what AMU means yet. We will hear it a bit, but just know that it's a relative mass, okay? So 12.01 is its mass. All right, so where do we get that? Most carbon atoms are carbon-12, which means that they have 6 protons and 6 neutrons. So their total nuclear mass is 12, okay? Carbon-12 means I've got 12 total particles or nucleons in my nucleus. 6 of them are protons, 6 of them are neutrons. Okay? And there is a small percentage of carbon-14 where you have 8 neutrons and 6 protons in the nucleus. And so its overall nucleon mass is 14. 6 plus 8 is 14. All right, so if I have mostly 99% carbon-12 and just maybe 1% of carbon-14, then if I add those together and average them, I'm going to get a value of 12.01. Okay, we'll talk about that. You're actually going to be able to do that by the time we're done here with this lecture. Okay, just remember the identity is determined by the number of protons. Okay, neutrons or electrons can add to the mass. Electron valence shells, have something to do with stuff. We'll talk about that too. But the neutrons don't determine the actual properties of the atom. All right. So why would we have carbon-13 and carbon-14 be considered isotopes? Because they have, pause it, different numbers of neutrons, okay? Carbon-14 has 8 neutrons, carbon-13 has 7 neutrons. What would a possible isotope of neon-20 be? Pause it, and we're back. And so an isotope might be neon-21, neon-19, right? Both of them still having 10 neutrons, but they would have different numbers of neutrons. Neon-21 would have 11 neutrons, neon-19 would have 9 neutrons, okay? So let's talk about mass number. Mass number is different than atomic number. Now, we're going through a lot of little terms here, and it's very important that you really get these terms straightened out because it's easy to get confused between mass number, atomic mass, the atomic number. There's so many different similar terms, so make sure you write these things down that you have them really squared away. This is mass number. Sorry, that's in red. That's hard to see. It's a total number of protons and neutrons that make up the nucleus, okay, of an isotope, of an atom, whatever. Mass number, total number of protons plus the number of neutrons, add them together, that's the mass number, okay? All right, so our mass number, why don't we count electrons? Well, remember I said in the previous lecture that an electron is like a dime in comparison to a milk jug gallon of a proton? Those electrons have such small mass, they're really insignificant, okay? So if I had a milk jug on a scale and I put a dime on it, you're not going to notice the difference. If you're holding it, right, you're not going to notice the difference. A scale might notice if it's a sensitive enough scale. But we basically say they're so small that it would take 1,840 of them just to equal one of the other. So it doesn't really matter if we add 1 electron or 2. Atoms only end up having what, like even some of the biggest ones, 118 electrons. So 118 does not even come close to making a significant impact out of 1,840 of them it would need, okay? Oops, sorry, let me go back there. All right, so if an atom has 14 protons, 14 electrons, 15 neutrons, what's its mass number? Don't pay attention to the electrons. Excuse me, doesn't matter in terms of this, right? Add up the 14 and 15, you got it, 29 is the answer. All right, so, oh my goodness, so hard to see this. This says hyphen notation. I'm so sorry, guys. I should have had this written in white so you can see it a little bit better. But this is called hyphen notation, okay? Hyphen notation. Woo! All right, hyphen notation. Mass number is written with a hyphen after the name of the element. So, for instance, oh, you can't see that either. Here we go. Uranium with a hyphen, 235. Okay, that 235 is its mass number. It's the number of protons and neutrons that are in the atom. So how do I know the number of protons of uranium? Well, you're just supposed to memorize it. No, you're not going to memorize it. You can look at the periodic table. Whoa, it's upside down. You can look at the periodic table. You can find uranium. So go, where's uranium? It's right here. Okay, number 92. 92 is the atomic number. It's a number on the periodic table, so it has 92 protons. If you want to figure out how many neutrons it has, you just take 92 from 235 and you got the number of neutrons, right? Then you've got the nuclear symbol. All right, nuclear symbol. Hey, by the way, any of you guys, okay, real quick, say nuclear. No, half of you did it wrong. Say nuclear. By golly, you're still not getting it. Nuclear. It's one of my pet peeves. People that say nuclear. George W. Bush. Oh my goodness. That guy did more for saying the word nuclear wrong than any other president. Yeah, anyway, it doesn't really matter. But don't say it wrong. It's nuclear, not nuclear. Okay. A lot of people say nuclear, including half of you. All right, so nuclear symbol. Superscript indicates the mass number, and the subscript indicates the atomic number. You guys are just still thinking like, who's George W. Bush? No, that's not what you're thinking, right? Not gonna do it. Not gonna do it. All right, yeah. All right, David Carvey. Anybody know him? Impressions of George W. Bush. It's amazing. SNL. I know you know SNL. There's one thing I said now, you know. All right, here we go. Nuclear symbol. The superscript indicates the mass number, and the subscript indicates the atomic number. Oh, hey, you can actually see it. So here we put a big symbol there. That's the nuclear symbol. U for uranium. I'm already doing carbon, right? A C for carbon. The top number is going to be my mass number. So if I did carbon 12, and my bottom number is my atomic number. So like that would be the carbon 12 symbol. That's the nuclear symbol. So we have the hyphen notation and the nuclear symbol. You need to be able to do those, okay? All right. So how do you find the number of protons and neutrons in an atom? Well, boom. The atomic number is the number of protons, right? Look at your periodic table. Look at that square. For the symbol, figure it out. It's right there. It's that number. How do you figure out the number of neutrons? Well, just take your atomic number, subtract it from your mass number. If the mass number isn't given, take the average mass and put it to the nearest whole number. So you're like, what's that average atomic mass? Well, it's the number underneath, okay? Hi there. It's the number on the bottom of each of these. So some of those are going to be decimals, right? So let's say we're looking at ruthenium, 101.07. Just make it 101, right? And then subtract from there. Okay. So how many protons, neutrons are in an atom of sodium? Write the nuclear symbol for this atom. Pause it. And we're back. Let's see if we actually have the answer displayed. There it is. All right, now these are offset. They really shouldn't be offset, right? So it should be Na, and then it should have the 23, and the 11 should be right underneath it. 11 is the atomic number, and 23 is the mass number. Very good. Okay, that's the nuclear symbol. All right, way to go. You guys are rocking it. Here we go, relative atomic masses. Now, I want you to think about, like, if we had a classroom of students, and imagine the smallest kid in the class, his name is Joey. Okay, hey, Joey, come here. All right, bring Joey over, and I'm like, Joey, how much do you weigh? And then Joey tells us how much he weighs. I'm like, all right, now you are the standard for this class. From now on, I'm going to weigh everybody in this class based upon you. And the kids are like, why are you talking in a New York accent? Eh? It's because I'm from Jersey. All right, no, I'm not from Jersey, but you know. All right, so now, hey, Samantha, you come here. You weigh 1.5 Joeys. Hey, Billy, holy cow, Billy, you weigh 2 Joeys. Relative mass, right? So deciding how much somebody weighs based upon their relative mass. If I choose Joey as the unit of measurement, then I can measure everybody in the class relative to Joey. And so everybody weighs a certain number of Joeys. Does that make sense? So that's what relative mass is. Relative atomic mass is basically, let's decide on how much something should weigh. Okay, it's not what, try that again. People decide, let's choose one particular thing as our unit of measurement, and then we decide how much something should weigh, or it does weigh, based upon that basic unit. Okay, so what did we choose? What was our Joey? Well, our Joey was the carbon-12 atom. Scientists decided that they wanted to use carbon-12 as the Joey. They wanted to use carbon-12 to weigh all the other atoms. But not just that, they decided, let's take 1/12 of a carbon-12 atom. All right, well, carbon-12 is made of 6 protons and 6 neutrons. Protons and neutrons don't weigh the same, but they're close. All right, so let's just take that value and say, let's divide it into 12 pieces. So 1/12 of a carbon-12 atom is going to have a mass of 1 AMU. Okay, so this says atomic mass unit, okay, or AMU. Okay, so, and sometimes you'll see this as just a U. Okay, so if you see the symbol U, that means the same thing as AMU. So the atomic mass unit, or 1 AMU, is exactly 1/12 the mass of a carbon-12 atom. That was our Joey. So now all of our other atoms we measure based upon that carbon-12 standard, okay? And so we just say, hey, let's compare it to the mass of carbon-12. And that's where we come up with the symbol AMU. I told you we're going to learn what AMU was, right? So that's what AMU is. Now, what about electrons? Well, the mass of an electron is essentially 0 when we talk about it in terms of an AMU because it's so small, okay? Now, electrons do have mass. Again, don't think that electrons don't have mass. Electrons have mass, but it's just really small, and so they just don't really factor in. Even for something like oganesson, which is 118, the element number 118, 118 electrons is nothing compared to even one proton. It doesn't matter, okay? So assuming if we look at our neutral atom, okay, we're talking about how many electrons do we have? Well, the number of protons is going to be equal to the number of electrons, okay? So if I have carbon 12, that means I have 6 protons because it's carbon. That means I've got 6 electrons. Just look at whatever element you have. Uranium, well, it's got 92 protons, 92 electrons. Number of protons, number of electrons are the same. Unless we give you something, we tell you it's an ion, which we're not doing that yet. It will come later. If we say it was an ion, then it would be different. But assume you're dealing with neutral atoms, number of protons is equal to the number of electrons. All right, so how many electrons in our neutral atom of calcium? Well, calcium, find it on the periodic table. All right, calcium, number 20. How many electrons? 20, because it's got 20 protons, right? All right, now, ions. Here we are, we're talking about them right now. We'll talk about them in a lot more detail later. We are introducing the idea here. All right, so remember, if an ion has gained electrons, it's called an anion. If it has lost electrons, it's called a cation. Okay, so cations are positive. Now, this works great for all of you like me that are cat lovers. You're like, oh, cats, they're so positive. I love them. Yes, cation, positive ion. Yeah, I get that. For those of you that are cat haters, you're like, what? No, I hate cats. It doesn't work. Well, guess what? I have something for you too. All right. Although this might hurt me to do it, here's our little cat. Get some ears. Okay. And then we'll do our little nose. Yeah, there's a little nose. And guess what? Positive. Oh, this poor cat's dead. So either you like cats, and that's great, or you don't like cats, but you can think of those little eyes being kind of like X's or positive signs in this case. You're like, cat eye, dead cat. That's so cruel. How could you even think that? It's rude. Love cats. All right, here we go. Again, anion, negatively charged. It's gained electrons. Cation is positively charged. It has lost electrons. So if we want to think about calcium 2+, okay, that 2+ means that it has a 2+ charge. It is a cation. Remember, cations are positively charged. And if it's a 2+, that means it's gain, or it has 2 positive charges. And 2 positive charges means that it's lost 2 electrons. What? Remember, there's protons and neutrons in the atom. If we think about calcium, let's think about that calcium center. That calcium center has 20 protons and 20 neutrons, okay? And that's its nucleus. Around the outside, it's going to have all these different electrons, right? Basically, around the outside, you could say, hey, it's got 20 electrons. But if it's a 2+ charge, that means it has 2 more positives than negatives. That means that there's only a total of 18 electrons around the outside, okay? Because 20 positives and 18 negatives gives me 2+, right? Got more positives and negatives, just like math. And so this is telling me that I've got a cation that have more protons than electrons, which means I've lost 2 electrons. The neutral atom would have had 20 electrons, right? The neutral atom would have had 20 electrons, but this one, this ion, this cation, would have 18 electrons, okay? Because it lost 2, and that's why it's positively charged, right? It doesn't have 20, it has 18. Does that make sense? So how many electrons are in a calcium ion that has a 2+ charge? Well, there's 18 electrons in that. Cool? Questions on that? Ask me when you get into class. Okay, here we go. Let's calculate our average atomic mass, okay? So, basically, the average atomic mass is a pretty easy calculation. There's a couple ways that you can do it. But the basic idea here is add up all, you guys know how to do averages, add them all up and divide by, the total number you have. But for atoms, there are so many different little particles, right? We can't add everything up that way. And so we have another method that we do. So watch this. All right. So what we're going to do is we're going to figure out its mass number or its atomic mass. Okay. And then the percent abundance. That's important here. To do our average atomic mass, we have to do something called percent abundance. And I'm going to show this to you quickly. Be prepared to have it on a test. So you may or may not see this on the test. But let's say I have 35% of a particular element. Let's convert it to decimals, all right? A relative abundance is called 0.35. Percent abundance would have been 35% abundance Relative abundance is 0.35. Then we're going to take that number and multiply it by the mass number. Okay, you'll see that here in a second. And then you're going to add all of these different, that's going to give you something called the relative mass. Then we're going to add all those relative masses together, and we're going to end up getting our answer. You are not going to divide by the number of isotopes, all right? So this is kind of an interesting way to do averages. Some of you guys have never seen this before. It's pretty cool. Let me show you real quick how you would do this. You know, like if you took 6 and 7 and 8 and 6 and 5 and 6 and 7 and 8 and 5. If you took those terms and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's do one more. Another 6. All right. And I took those terms, I added them together, I'd get a value, and I would divide by 10, right, to get my average. Well, do you know what would happen if instead of doing that, you looked at how many terms you have? I got 1, 2, 3, 4 6s. Okay, you got 4 6s, 1, 2 7s. I've got 1, 2 8s, and I got 1, 2. We'll put our 5s up there so they're in order. 2 5s. Okay. Well, what's my percent abundance of each of these? Well, I've got 20% 5s, 40% 6s, 20% 7s, and 20% 8s. So what's my relative abundance of each of these? 0.2, 0.4. 0.2, 0.2. Oh, okay, so let me figure this out. 0.2 times 5, 0.4 times 6, 0.2 times 7, 0.2 times 8. Now here's the cool thing. If you do that calculation, whoa, hide up, Laura. If you do this calculation, hide away, then these numbers, if you add all those numbers together, that's going to be the same answer as if you add all of these together and then divide by 10. There's 2 ways to do averages. You just never really had to do it this way before. This is kind of a different way, but it's the same thing. You get the same value. Take your percent abundance by the term and then add all of those together versus add all the terms together and then divide by the total number of terms. So what we're doing by figuring out the average atomic mass in our calculations for chemistry is we're doing this method, okay? Because this method works with the percent abundances, which is what we have. We can take a sample of material and we can look at how much carbon-12 is there, how much carbon-14 is there, and we can do that with mass spectrometry and look at how much of this particular substance there is based upon how many particles are there. It's kind of cool stuff. So anyway, you don't have to worry about that right now. But this is the form that we're going to be using to calculate our answers. All right, so I just wanted to show that to you. You can practice that, do that on your own. I'm not going to show it to you now, but if you're curious and you don't believe me, you try it. You'll be like, yeah, well, that really was true. That's cool, Box. All right, so here's an example with sulfur. I've got sulfur 32, sulfur 33, sulfur 34, sulfur 35. I've got 4 isotopes of sulfur, and they have different percent abundances, okay? They have different masses, and then different percent abundances. Most of the sulfur on this planet is sulfur 32. The second most popular is sulfur 34. And I apologize, these things are not quite lining up. Then you have 0.76% of sulfur 33 and 0.014% of sulfur 35. Turn all of those into decimals. Oh my goodness, it's in blue and there's no way you can see it and it's not lined up either. I'm going to do 0.95, 0.0076, 0.0422, and 0.00014. Okay, convert those to their relative abundance, multiply their masses. So just multiply by 32, 33, 34, 35, and there's no way you can see that. But these numbers are 30.4. Ooh, I can barely see it. 0.2508. 1.4348, I think, and 0.0049. It's like invisible writing. Okay, you can probably see the green there. All right, so you take these and you add them up, okay? This one plus this one plus this one plus this one, and you get 32.09, okay? That is the the average atomic mass of sulfur. And if you look at sulfur on the periodic table, you'll see it says 32.07. All right, pretty close. I do want you to know that different periodic tables are actually going to give you different answers sometimes for some of these masses. And that has to do with different groups doing some of these studies. One scientific group will go and it'll make a study and come up with an answer. Another group will say, you know what, they didn't do their study quite right, and we actually think that the mass is closer to this. So that does happen. Here we go. I will let you try this one. Boron has 2 naturally occurring isotopes. Boron 10, 19.8% abundance, and boron 11, 80.2% abundance. Calculate the atomic mass of boron. Okay, so you should be able to do that. Figure it out, pause it, and we'll probably do this one in class. I don't think the answer is actually on here, so we'll come back and do that in class. All right, so here is our review of terms. Well, you guys know what an atom is. Oh, my llama fell. All right. Be gentle. The llama. Be gentle. We don't want the llama to fall. Found that in my class last year. That has entered as now a permanent part of my life. Yes. All right. The atomic numbers, the number of protons. And that's going to be symbolized right here on the periodic table's element symbol, right? That's what defines the element. Remember, the number of protons is equal to the number of electrons. The mass number is not found on the periodic table, okay? You will not find the mass number on the periodic table. This one down here is not the mass number. The mass number is only one where you can get that answer by knowing the number of protons and knowing the number of neutrons, okay? We might tell you the mass number is blah, 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 but it's not on the periodic table, okay? Now, then, yep, that's what it's saying. Periodic table is only listing the average atomic mass. And by the way, sometimes you're going to hear the term atomic weight, not usually in what we're talking about, but other texts will use that. Same thing as the average atomic mass, okay? And remember that we can use AMU or U as our symbol for talking about a single atom, okay? So it's important to understand. If I asked you for the mass of a single atom, you would express that mass in terms of AMU. Okay, so keep that in mind, all right? Because AMU is a really small number. Again, it's 1 AMU is equal to 1/12 the mass of a carbon-12 atom. So make sure you are clear with that, okay? All right, so atomic mass versus mass number. What's the difference? Remember, atomic mass is an average of all the different types of isotopes that exist, right? It's the weighted average of the atomic mass of the naturally occurring isotopes of an element. Average isotopes, okay? That's what goes in there. And remember that the average atomic mass is not going to be a whole number typically, right? It's going to have decimals at it because it's an average of all the ones that actually do exist. The mass number is always going to be a whole number, okay? And it's the mass for a particular isotope of a single atom, all right? It's for the mass of an actual atom, okay? Not a weighted average of all the different atoms. It's the mass of an atom, okay? And remember, you just count the protons and neutrons to figure that out, and it's a whole number. C12 would have a mass of 12. C14 has a mass of 14 AMUs, right? Carbon has an average atomic mass of 12.01 AMU because carbon is, when we find carbon in nature, if I were to get a chunk of coal and I'd pull out all the carbon, some of it's going to be carbon-12, some of it's going to be carbon-13, some carbon-14. So when I average all those masses up for those different things, I get 12.01. Okay? All right, so hey, we've done it again. We have covered another great section of our textbook, and we now know some amazing things. So let's check out our objectives. Let's review them. Can we now describe the property of protons, neutrons, and electrons? Yeah, right? Positive charge, neutral charge, negative charge, massive, massive, not massive, okay? Center of the nucleus, outside the nucleus, right? Things like that. Calculate the number of protons, neutrons, electrons in an atom. Yeah, we can do that. Number of protons is equal to the number of electrons. The number of protons found on the periodic table. The atomic number of neutrons can be determined by subtracting the atomic number from the mass number. We got that. And can we calculate the average atomic mass? I think you can. You now know a whole new way of doing averages, and you can now multiply relative abundance by the atomic number, the mass number, and you're going to be able to figure out the overall average atomic mass by adding them up. Okay, cool stuff. Yeah, look at you. You are successful because you can do all of those things, okay? So, yeah, way to go. You can state the charge, mass, location, each of the subatomic particles. If I give you a nuclear symbol like Na, right, you can determine the number of protons and neutrons in that atom because I would give you the nuclear symbol, not just the Na, but also, remember we had like Na23, right? Nuclear symbol Na with the 23 and 11. You can now tell me how many protons and neutrons and electrons, right? And then if I give you protons, neutrons, electrons, you can create one of those nuclear symbols. And given the masses and percent abundances for the isotopes, you can calculate its average atomic mass. maybe with a little practice, maybe that's going to be what we're going to be doing once you come into class. Yeah. Okay. All right. So there we go. Another amazing day, another amazing lecture, a lot of fun and a lot of things we learned. You know, what this is all about is telling us a little bit more information about the atom, that we have this amazing periodic table. We're just starting to get into this periodic table and starting to figure out how cool it is and how we can get fun little pieces of information off the periodic table. And it also is really important for us to understand that the properties of an element are based upon the number of protons. Okay, the number of protons determine what an atom is for a particular element. And so you know, if you change one proton in an atom, you've changed it to something completely different. I mean, think about the difference. Like if I had platinum or gold, right? And I've got, you know, one proton extra in platinum all of a sudden turns it into gold. One extra proton into gold all of a sudden turns it into mercury. Think about the difference. Gold is yellow and it's solid at room temperature. Mercury is liquid and it's silver. So like, whoa, one single proton can change the properties. Yeah, it's so cool, isn't it? Huh, it's amazing. All right, chemistry's amazing. You're amazing. You have a great day. God bless you.